Hi folks, this week we're going to focus on the intersection of three planes. So far in terms of intersections, we've looked at two lines, we've looked at a line and a plane, and we've considered two planes. Now, what was interesting about the intersection of two planes is there was no way for two planes to intersect at a single point, okay? When they intersected, as long as they weren't the same plane, they would intersect in a line. Now, if you think about it, it's not too surprising because when you're solving a system of two equations and two unknowns, we say you need two pieces of information to solve for two unknowns, hence the two equations. So when you had two equations with three unknowns, it shouldn't be too surprising that we weren't able to find a single answer, okay? But presumably, if we're working with three pieces of information, in other words, the intersection of three planes, might we be able to find a single solution? So ideally what you would do now is you'd stop the video and you'd take three pieces of paper, three pieces of cardboard, and try to figure out all the possible scenarios that one could have when it comes to three planes. So we know with two planes, they could be coplanar, essentially the same plane, coincident, okay? They could intersect in a line, as we just talked about, or they could be parallel and distinct, where they never intersect. All right, so see if you can come up with all the possible scenarios for three planes. All right, so I'll start up in a second if you want to stop. Okay, so we're back and let's see all those things that we can come up with. So I think what I'm going to do is I'm going to try to start with all the scenarios where the planes could be parallel, or at least some of them can be parallel. And so one possibility is that all three planes are coincident. So in other words, if I had three equations, they actually all represent one plane, okay? As we had, two planes being coincident, okay? But if I stay along these lines, what if I have two of them that are coincident and another one that's parallel and distinct? Well, here I realize that even though these two intersect in a plane, this one being parallel and distinct means there's no intersection between all three planes. Okay, so there's a second scenario. Again, continue along this line. What if I have three planes that are all parallel and distinct? Okay, so there's a third option. All right, let's keep going. Well, what if I stick with this idea of having two planes that are parallel and distinct, and I have another one which is not parallel to the other two? I realize that I'm still not going to have any point of intersection. I can't, because these two planes are parallel and distinct. All right, but what if I have two planes that are coincident and a third plane? So these two are parallel and coincident, okay, but a third plane that's not parallel to the other two, then automatically, hey, look what I have, just like what I had before. It turns out to be like the intersection of two planes, in other words, a line. All right, so far, all the possibilities involving, all or some parallel planes, we've got five of them. We've got the three of them coincident, two coincident, one distinct, all three parallel and distinct, two parallel and distinct, another one not parallel, still no intersection, or two of them that are coincident, the other one not parallel, line of intersection. Okay, so far that's five scenarios. Okay, let's now try to think about what would happen if none of the planes were parallel to each other. Okay, well, hopefully you came up with this thing here, and this answers that question that I asked. Can we have a single point of intersection? Maybe this way, give you a bit more light. And you realize that there you go. When you've got three planes, you can have a single point of intersection. So notice these three planes, none of them are parallel to each other, and the only intersection occurs at that corner there. Okay, so there we go. We had what we were looking for. However, this is not the only way they could behave if none of them are parallel. What if you had something like this? Okay, now let me bring it, give you another view of it. let's say you had none of them parallel, but look at what happens. They actually intersect in a line. You see this line here. They all intersect in a line. Okay. What about this scenario? What if you have the three planes that form essentially an infinite triangular prism? Okay. None of them are parallel, but you see that there's no intersection. You know, 2 by 2, they intersect, but there's no points of intersection for all three planes. Okay. So if you counted there, we had 8 possible scenarios. So significantly more than all of the other ones that we had considered the week before. All right. So let's take a look at the scenarios here. And let's start with the ones where we have some parallel planes, because these are all things where you should be able to get a sense of the scenario just by looking at the equations. And the reason I can say that is that when you have parallel planes, their normals have to be parallel to each other. Okay? Not just that. If they're parallel and coincident, you know the d values are also going to be offset by the same factor. All right. So if you take this scenario where you've got 3 coincident planes, well, what would that look like? Well, it would look something like this, where you have 3 equations. Look at the normal vectors, 1, 2, -1, 2, 4, -2. You see that the normal vector in equation 2 is twice that of the normal vector. And here that one's 5 times the normal vector in equation 1. Okay, but not only are the normal vectors all parallel to each other, look at the d values. Okay, now notice here, you're going to start to see that I'm going to be putting those d values mostly on the other side of the equation. And I think you'll see why when we start solving some stuff. You'll notice here that the factor that connects the normal vectors is 2, and 3 times 2 is 6. The factor that connects these two normal vectors is 5. 3 times 5 is 15. Okay, so essentially these all represent the same plane. This scenario is going to be represented by something very similar, because what I see is, take a look at planes 1 and planes 3, same ones as before. These are parallel and coincident. But if you take a look at the second equation, we see that the normals are parallel, but this doesn't differ by the same multiple. 3 times 3 is not equal, 3 times 2 is not equal to 1. Okay, so you have 2 coincident planes and one that's parallel, but not coincident. Okay, so without having to do any work, I'm able to determine the intersection, or at least in this case, the lack of an intersection. Very similarly here, we're going to have 3 normal vectors that are parallel, but the d values don't differ by the same factor as the normal vectors. All right, let's keep going. Something like this, where I have 2 that are parallel and distinct. So hopefully you're thinking what I should be seeing in my equation. So here, if I look at the first and the second, I see 2 planes. Look at the normal vectors parallel, but the d values don't differ by the same scalar multiple. Okay, hence parallel and distinct. And then some third vector that's not parallel. But in the end, because these were distinct, I can't have any intersection. This is the one where you're going to have to do a little bit of work, okay? Because if I take a look at a scenario, which is very similar to this one here, I notice if I look at the first 2 equations, these 2 represent the same plane. These 2 are coincident, but then this one is not parallel. So essentially, you're going to be solving what we solved last week. You can pretty much forget about this plane here because it represents the exact same plane as number 1. So you're going to be solving the intersection of these 2 planes. And you'll follow the algorithm that we learned last week for the intersection of 2 planes. Okay? So what's nice about all these scenarios is either I can tell right off the bat what the answer is going to be, or in this scenario here, where there is some algebra to do, Well, I'm just reverting back to the algebra we already learned, because this system is equivalent to solving the intersection of two planes. All right? So in terms of the algebra, where we're going to be putting our focus is on solving these three scenarios. Okay? Now, this is the one that's going to end up being the most important, because when you're, using this in the context of applications, you're usually looking for a single unique answer. All right. But we're also going to see, how does such an equation work out when you try to solve it? And it turns out to either intersect in a line, in other words, infinitely many points of intersection, or this idea of the triangular prism where there's no points of intersection. So the next couple of videos are just going to go through examples where you have these different scenarios come up and how you can interpret them. Okay? And what's nice about what we're going to be seeing this week is that the methods we're going to use are all going to be based on methods that we use to solve simpler systems of equations. All right, that's it for this one.